with dua. Yeah. Bismillahirrahmanirrahim. Allahumma sholli ala Sayyidina Muhammad wa ala ali Sayyidina Muhammad. Allahumma ighfir li dhunubi wa li walidayya warhamhuma kama rabbayani shaghira. Rabbi shrah li sadri wa yassir li amri wa hlul 'uqdatam min lisani yafqahu qawli. Rabbi zidni ilma warzuqni fahma. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar. Amin ya rabbal alamin. Okay, so today I will deliver the module 4, and then I'm here with Dr. Lucia. Say hi to Dr. Lucia. Please help me if I miss something today. I'm gonna share screen for the module E4. Can you see my screen?
I can see.
Okay, thank
Dr.
you.
Vera,
Yes? Yes, Rico?
screen.
I can see.
Sorry, Rico, I cannot hear you. Did you say something? No? Okay, I will continue. So today we will discuss about the geometry optimization, the model A4. So before we only calculate the atom, but today we will calculate the molecule, the very simple molecule. So we start from the objective. The objective of module A4, there is two objectives here. The first is distinguish the physical and computational problem. And this will be, the cognitive is C2 and the dimensional is 2. So I think all of you already good in the distinguish the physical and computational problem because you already try it for module 1 to module A3. And then the second objective is apply two different calculation routine. So, apply two different calculation routine for geometry optimization of diatomic molecule. And for additional, we will identify Cartesian coordinate and Z matrix. So today you will learn about two new calculation routine for geometry optimization. And then the study case is also new because before you only calculate the atoms, now you will calculate the most or the simplest molecule, the diatomic molecule. And then if the previous calculation, you only know about the Cartesian coordinate, now you will know the Z matrix. So we will see how is the Z matrix. Okay, so we will continue to introduction. Here, recall that the Born-Oppenheimer approximation, or BOA, fix the position of the nuclei. So the Born-Oppenheimer approximation fix the position of nuclei. Consequently, Born-Oppenheimer approximations change the distance between the nuclei. From the variable, we can see here the variable can be R1, R2 until Rp, while the index P is the number of the nuclei to the parameter. So we only have parameter. We no longer have the variable R1, R2, and extra. We only have parameter. That's the Born-Oppenheimer approximation, because this approximation fixes the position of the nuclei. We no longer have the variable of the R. We only have parameter here. And then the introduction of Hohenberg-Kohn theorem, followed by replacement of TC with the quantum equation, makes the parameter R determine the external potential energy function, or V external. So the first information is BOA change the nuclei parameter, from variable to parameter. This is the first important information. And the second one is quantum equation make the parameter R determine the external potential energy function. Why we call it V external? Because this is the potential energy that comes from other than electron, because it's from nuclei, so we call it external. And then the external energy dictates the electron density function, or ρr, which replaces the electronic total wave functions. So we no longer use C, that the function of R1, R2 until RQ, where Q is the number of electrons. So P is the number of nuclei and Q is the number of electrons. So the V external is important to dictate the electron density function. Okay, this is the third information. Okay, and then in the molecular system, only one combination of R gives rho R, which represent the ground state of the molecule. So in the ground state of the molecule, we only have one combination of R. Finding that particular of R combination is called geometry optimization. So what is geometry optimization? The geometry optimization is finding the only one combination of R that gives rho R, which represent the ground state. So in the ground state, we only have one combination. How to find it? We need geometry optimization. So that's why today we will calculate the geometry optimization. So this one is already explained by Mbak Rizka in the second meeting. You can Can you see the slide? Yes, okay. So you can refer to slide 24 and also 25. Here there is explanation that there is a bijection between C in the ground state and rho. So we can use the density functional here. And then energy is the function of the rho zero. So one of the component of the energy is VNA, or we can call it V external. And then in the V external, there is only one parameter R that give rho zero. So we have three bijection here. What is the bijection? Bijection is one correspondent. So they are pairing. So C ground state have one correspondent to rho zero, and then rho zero has one correspondent to the R zero. So the R zero will give the rho zero in the ground state. So the basis of the geometry optimization is we want to find the R0. The R0 is the position of the nuclei. In the case of molecule or diatomic molecule, so the R is the distance between first atom and the second atom. So that will be the R. Okay, we will come back again to the module. So here, as the result of Born-Oppenheimer approximation, it is possible now to find the ground state of molecule based on the geometry optimization. So we will practice geometry optimization for simplest molecular system. We will use homonuclear diatomic molecule. So there is two atoms that has the same nuclei, where there is only one combination of R here, R as the parameter, which is the distance between the two atoms in molecule. So for example, this is atom hydrogen, this is hydrogen. So the R will be the distance between two hydrogen molecule. If this is the oxygen molecule, and then the second one is oxygen molecule, so the R will be the distance between two oxygen atoms. And then we will prove that there is only one R that provides the ground state of the molecule, where the distance has reached its optimized geometry. So we need to use optimized geometry to find the R parameter in the ground state, and we will find only one R. Okay, from here, is it clear, or is there any question? No? Okay, is it clear? Okay, thank you. So we will continue for prerequisite. The first one is complete the module 3 And I will remind you about the report. So we extend the deadline of the report for tomorrow. So please don't forget to submit your report. And then the second one is access to CRC Handbook of Chemistry and Physics. So remember what Dr. Fabian said, that never went to a website called LibGen because it will provide you free books. So yeah, don't go there. Go to the LibGen. Okay, I will continue for project description. So how many molecules you will have to calculate? There is a 5 homonuclear diatomic molecule. First one is H2 molecule. The second one is O2 molecule. The third one is N2, and then F2 and Cl2. So you have 5 molecules in your project description. And then we will use 2 methods. The first one is Hartree-Fock, and the second one is B3LYP. And then we will use 3 kind of basis set. So I think all of you are familiar with this method and this basis set, and you already know what is the difference. And the objective, so the goal, your objective is finding the optimized bond length, or R0. And we will perform 2 routines. First is optimization using keyword OPT, and the second routine is scan. So we will use keyword scan here. With the initial distance RI, or R initial. The RI is the closest possible distance. So you can check how long is the closest possible distance that you can calculate. And then there is a note here. So I think it is clear for OPT, but for routine scan, the final distance will be, I think this is not R0, because R0 are the one that we want to find. We will find the R0. So this is the R initial. So R final is R initial plus 5 angstrom. So I will demonstrate to you later. In the optimization or OPT routine scan, we only need the R1, R initial. But for the scan, we will perform single point energy calculation. So we will calculate for each distance. For example, the closest possible is 0.6. We will calculate 0.7, 0.8, and etc. So we will make a point until reach the 0.5 angstrom from the closest possible distance, and then we calculate for each point. Okay, that's the project description. And now results and discussion. The first one is briefly explain what SGF done. So you can explain about what this part is about, and then, for example, this is a 7th cycle. What is the cycle means in here? So just explain it. You can Google it or maybe use ChatGPT to find the explanation about this one. Okay, and then for second one, you need to explain about what is the main indicator that the routine OPT has complete. So what is the indicator that my calculation of optimization geometry has complete? Is it the poetry or etc.? So you will know the main indicator. And then the third one, you will tabulate the number of SGF done and job CPU type. So you will count how many SGF done and then the job CPU type. Okay, so just fill the table. So this one will be the number of SGF done, and this one will be the job CPU type. And then the fourth, briefly explain. So after we perform calculation optimization and also scan, you will have comparison analysis. So you will explain what is the similarity between these two routines and also the difference between the two routines. Okay, and then the fifth, fill the following table with the worst accurate method and the best one. So which one is the worst and which one is the best? The lowest percentage. So which one is the worst accurate? The least percentage or the higher percentage, the highest or the lowest percentage? Which one is the worst accurate method? Which one?
Which one, guys?
The worst, the highest or the lowest percentage? So the closest to experimental value or the farthest?
Can you repeat again? Showing like
Okay.
The lowest appropriate method is the highest percentage.
Okay. Can you repeat, Rico? Because I cannot hear clearly. Oh, there is microphone there. Cool.
Maybe the worst accurate method is the highest percentage error percentage.
Yes, correct. So the worst will be the highest percentage, error percentage. So the best one will be the lowest error percentage. Thank you. Who is that? Who? What is your name? Sorry, I cannot hear you.
My name is Putri.
Who?
My name is Putri.
Ah, Putri. Okay, thank you, Putri. Okay. From here, is it clear? Or you have any question? No, if there is no question, I will continue for demonstration. So please prepare your Gauss view. Sure. So please let me know if you are ready with your Gauss view. So can you see my Gauss view here?
Yes, I can see.
Okay, thank you. So first we will calculate the optimization routine. So we will do the easier first, then the complicated later. Okay, is everybody ready? Okay. Okay. First, I will perform hydrogens here. Just click. You can click in this element or in here, element fragment, and then hydrogen. I just this one. Just click here. Okay. And then we will set the distance between two atoms. So we can make the label here. So this is first H atom and this is the second H atom. We want to set this one, the R initial. So you can use the builder and modify bond. So builder and modify bond. And click the first and the second H atom. Here, you can use this one to adjust the distance or just filling in here. For example, 0.5 or 0.3 or 0.6. So I will choose 0.6. Okay. Can you follow?
Dr. Vera,
Yes.
so 0.6 is just a random number that we put in there. Is it up to us?
Yes. Because this is the closest possible distance. So we just try first like 0.6 or maybe 0.3 because we don't know yet which the distance is the closest as possible that we can make the geometry optimizations calculations.
Okay.
So if we increase the distance, example 0.9, you'll see the distance in here also become higher. Okay, so we will start at 0.5 and then okay. And we go to calculate, Gaussian calculation result, set up. And here choose the job type, choose the optimization. Here you can see the optimized to, there is a minimum and TS, but today we use minimum. We will optimize the minimum and we use default force constant. And then for method, you can use hard revoke or TFT. So I will choose TFT. And for basis set, we have 3 options. The first option is this one, and then this is the second option. And the third option will be 631G, D, and B. Okay, so you have 3 options of basis sets. But now I will use 631G DP. And the charge is, because it's neutral, so I just put the charge 0. And then the spin singlet from the module 1, module 2, and module 3, you already know that we need to consider the spin multiplicity for the calculation. So for me, I already checked that the spin multiplicity of hydrogen molecule or H2 is singlet. But for the other molecule, you need to check first whether it is singlet or triplet or quintet, which one has the lowest electronic energy, or the more negative is the ground state. So for example, in my case, I calculate the H2 molecule. I already calculate the optimization for a singlet, and I also perform the calculation for triplet. And I compare the total electronic energy, and I found that the singlet has the more negative electronic energy. So the ground state will be hydrogen, spin multiplicity singlet. So I choose singlet in my calculation. So please pay attention to spin multiplicity of molecule. And then just uncheck here. So submit, save. Yes. So I got the error. Why? You can check the error. So The error is because my atoms is too close. So 0.5 cannot be the R initial. So we have to change the R initial. We come back again to our model. So here, builder, modify bond, and click the first atom and the second atom. And I will set 0.7. Because we want to find the closest as possible. Okay. And then we calculate Gaussian calculation setup with the same method. Then just submit the same. So now it ran perfectly because I choose the right distance. So you have to find which distance are possible. You can also not only like 0.7, you can also like 0.65 or yeah, it's up to you to define the R initial. And then we can open the result here. Can you see this one? If not, you have to set something here. So I will close here. File, open. So whenever you open the log file, please make sure that you check this one. Read intermediate geometries. If I uncheck this one and then click the log file, there will be no intermediate state here. But if I checklist this one and then open the input file, I will find the number of iteration or the number of the intermediate states. So you see the difference? Like the first one, the second one. So we will use this one. So I will close the other one.
Dr. Vera,
Okay.
you mentioned before that they have to check the spin multiplicity of the molecule, right?
Yes.
And when they check, do they have to tabulate it and collect it together with the assignments, or they do it separately in their own paperwork? They don't. Do they have to collect it also or not?
No, they don't need to include in the report because it's the basic, calculation. They need to consider it, but they don't have to put in the report. So the report is the one that the molecule with the lowest energy of the spin multiplicity. Okay. Now, from the optimization calculation, you need to explain the SGF done here, and then you have to make a list. What is the main indicator that routine optimization has complete? So here we can see from the result and then summary. Here there is this is written here that optimization complete. And then if you click here, 1 of 3, here also, this is the optimization step 1 of 3 steps. This one, sorry, this one is 2, step 2 of 3, and then this one, the complete one. And we cannot click the thermo, but we can click the OPT. So the OPT gives information about the step number. So there is a 3-step number of iteration. And if you check the stream output file, you will find there is this. I'm looking for SGF done. So this will be the first SGF done with the 7th cycle. And then the second SGF done with the 6th cycle. And then the third SGF done with 4 cycle. It means that this step is the number of SGF done. So to find the R0, it needs 3 iteration or 3 SGF done calculations. And here the step number, and then this is the convergence criteria. So each criteria, there is an information whether it is converge or not. So this is all of converge. So we can, and then you can also check the job CPU time here. Okay, and now you have 3 steps. So which one are R0? The R0 is the latest step. So 3 of 3 is the latest step. So you can just click these 2 atoms and you will find the bond line. This is 0.74280. So this is the distance between H1 and H2, or R0 that we're looking for.
Dr. Vera, I think you need to move
Here.
a bit in the middle.
Sorry?
The output file before, yeah.
Okay.
Maybe you need to move it a little bit to the middle because the number is blocked by.
Okay.
Yeah. Okay.
Okay. Can you see here?
Yes,
So when you click it, you can see the bond length here. This is the number that you have to tabulate later. So that's the first routine, the optimization routine. You can also see in here the result, and then just click the optimization. And you will find the plot. So this is the optimization step number. And the total energy. So this is the first step. And then the second step, the energy is decreased. And the third step, and it is stop in the third step. So we need 3 steps to optimize H2. Okay, there is question. Any question?
Yes, Dr. Vera. The bond length that you showed before, 0.7 and so on, is that the R0 or Ri? Can you hear me?
Sorry. Okay, I can hear you. So this one,
Yes.
yes, Dr. Lucia.
Yes, this one.
This is the R0. This one is R0 because this is the latest step. If you want to find the R initial, you have to go to the first step. Like this is first step of 3. So this will be the R initial. Because in the initial I set up 0.7. But and then we optimize it, and then we found that the R0 is 0.74.
Okay.
And there is information in the result summary that this calculation is complete. If we choose the wrong step, there will be no information that our optimization are complete. So make sure that we choose the latest step. Okay?
Okay.
Okay, how about in ITERA class? Okay. How about the UNAIR class? Can you do the optimization? Why they are freezing? Okay, from UNAIR, is it clear? Can you follow?
Yes, Dr. Vera. Yes, Dr. Vera. Oh iya, Dr. Vera.
Okay, sorry. I just got kicked. Okay. Let us continue. Okay, is there any question from UNAIR class? Is it clear? Hendra, is there any problem in their calculation?
So now, I haven't found any problem with them.
Okay. Okay, good. Now I will start the second routine. What happened to this one? I can close it. Okay. Now we will continue to the second routine. So please pay attention because this will be more complicated than the first one. So new molecules. Oh. This one. Wait, I need to set up this one. So can you see my two windows here?
Yes, I can see.
Okay. Like the first one, we just click the folder and choose element fragment, choose hydrogen, and just click here. So the first task will be set the R initial. So we just use folder and modify the bond. And then click. We'll view the labels. Click the first and the second atom. So I can sorry for inconvenience. Okay. Okay. I will repeat. So just click the atom 1 and then atom 2. And then we set the R initial here. 0.5. Actually, I already checked. So I checked a 0.3 and then 0.4, but it's error because the atom is too close. So I choose 0.5. So you can check later for each atom, which is the closest possible distance. And click OK. And then you go to tools and atom list. Tools, atom list. Can you find it? Okay, and click the atom list. And here, please highlight the first and the second row. Please highlight here. So this tag, the first hydrogen is tagged by 1, and then this is the second one. So we put the second atom here, and this will be the bond between the second hydrogen with the first hydrogen. And then this bond is the one that we want to scan. So please choose RxN/scan here. Okay. So there is a 3 option, no, yes, and Rx scan here. So make sure that you choose the right cell. So this is the OPT one, the XX scan. Okay, and just close. And we go to calculate, Gaussian calculation setup. And choose the job type. In here, you'll find there is a new keyword here. So after we edit on the atom list editor, and then we put the Rx/scan, there will be a new keyword here. The keyword is scan, the rigid scan. Actually, we can choose 3 kinds of the scan, but now we only use the rigid scan. So this is rigid and relax using Z matrix, or relax using redundant coordinate. But today we will choose the rigid. And you will put in here the number of steps. So how many steps that do you want to calculate? 10, 20. So you will have 20 calculation. If 10, so you have 10 point of calculations. So this is the number of steps. And then this is the step size or interval between the steps. So you can put 0.1, 0.3, or 0.5. It's up to you. But make sure that the step size of all molecule is the same. So you are free to choose the step size. So I will choose the 0.1. And the start value is 0.5. And I want to have the number of steps is 50. So this is 0.1. So this will, the end value will be 5.5. So we start at 0.5 and then 50 step multiplied by step size 0.1. So the calculation will end up in 5.5. So this is in angstrom. Like we start from 0.5 angstrom and we add it with this one, 5 angstrom. So there will be 5.5. Since I choose the number of steps is 50, so the step size will be 0.1 angstrom. Okay. And the method, you can change to the DFT, and then the basis site G and B, and spin multiplicity is singlet. And I need to uncheck this one. And we see the preview. Okay. Can you see this one clearly? Is it too small? So you can see that there is a different in the input file here. So this is will be the keyword, and then this is the title card of title, and this one will be the charge, and this is the spin multiplicity. So up to this, I think it is the same with our previous calculation, but the new thing is the coordinate. In your previous calculation, you will see that the H atom is located in the coordinate Cartesians. Means there is information in here. For example, the first H atom is has like the position in the x-axis, y-axis, and z-axis. Remember? And also the second H atom. But in here, you cannot see the x, y, and z axis because we use the Z matrix. So we no longer, for scan rigid, we no longer use Cartesian, we use the Z matrix. So this is the first H atom, and then this is the second H atom. The second H atom with the first H atom has a distance of B1. So how much is the B1? B1 is 0.5. This is the initial R, or the initial distance that we set between two hydrogen atoms. And here there is a keyword scan. So what is the mean of these two numbers? So this is the initial distance, and this is the number of the step, and this is the step size. So I will perform the scan calculation starting from 0.5, and then I will scan for 50 points, and each point has a interval or step size 0.1. So for the first step, it will be 0.5 plus 0.1. So the first step will be 0.6, then 0.7, and extra. Okay, is it clear? Okay. So make sure that you already define this like number of steps, step size, and the start and the end of value. And then we submit. So we use S. Save. Yes. So because I choose 50 points, it took longer. So the more step you choose, the longer it will be. Okay. And choose the log file. Okay. How about your calculation? Is it success? Hendra, how is their calculation? They still calculate?
They are doing calculation right now, and I think they are doing from where I'm looking.
Sorry, I cannot hear you clearly, Hendra.
Right now they are doing calculation and they are doing pretty good so far. And I still haven't found any problems with them.
Problem. Okay. Super.
Thank you.
Okay. How about you guys? Okay. Can you follow? Okay. So now we check our result. So here there is a 51 number of steps because the R initial and we add with 50 steps. Sorry. Are you finished with your calculation? If not, we will wait. How about you guys that join online? Did you find any problem? For Olive, Ayo, Bintang? Okay, can we continue? Okay, we will continue. So click the result. And here, if you perform scan calculation, there is a scan here that you can click. So you can see the plot here. So this is the scan coordinate. So we start from 0.5 and end up in 5.5 here. So this is the point that we do single point calculations. So this is the first step. In 0.5, we calculate the energy, and then we move the atom to the 0.6 because the step size is 0.1. And then we move in here, the third one. This is 0.7. And you can see the, sorry. You can see the energy here. So each step, this is 0.5 with the total energy in heart rate is minus 1.10. Then just click the second 0.6. And then the third one is 0.7. And can click. And you can see in here, the atom is also moving. So from here, this is 1.3. So the distance between this one and this one is also 0.3. So if we move here, it will 0.4. So now the question will be, which one is R0? The R0 is the point that has the lowest energy, the lowest total energy. So if we see here, there is a 2 point that might be the R0. Whether it is the third step or the fourth step. So we can check the energy. So in here, the energy is 1.177, and in here is 1.176. So which is the lowest? The third or the fourth step? The third or the fourth? I can see it. The third one. Yes. So this would be the R0. Okay. So you can find the similarity and the difference from the graph, and also maybe for the time consuming. And yeah, you can after doing a both calculation, you know which one is easier and which one is faster, which one is effective in terms of time. Okay. Is there any question? Is it clear?
Clear.
Okay, if it's clear, then I will move to your assignment or your report. Okay. So for the first one, it's already clear that you just explain the SGF done. And then the second one is see what is the main indicator of the routine optimization has complete. What is the indicator? Just write down here. And then, okay, the number of the SGF done. So the number of iterations in the optimization step and job CPU time. I think 1 until 3 is very clear. And here for the 4, so you need to tabulate first and then see the difference between the two routines. So in my case, I already have a 4 calculation. So 2 calculation of optimization and 2 calculation of scan. So before I make a calculation, I define the nomenclature. So the first is the calculation type. So O, scan. And then the second one is exchange correlation. Okay, can you see it?
Yes, I can see it.
Okay, so this is the exchange correlation. A will be H. So for example, I have a file name OB1. It means that I do optimization or OPT calculation. sorry, this will be, should be open. And then B mean B3LYP and 1 mean 321T. And then I make the tabulation. So the molecule is H2 and I look for the experimental value of the bond length in the CRC handbook. I found out that the distance, the R0 from the experimental is 0.74144. And then I tabulate the scan. So, okay, I will demonstrate to you how to tabulate. So now, file, open, I will open the scan file first. For the SA1, file open. SE1, open. This is result. Scan. So from here, I found out that the lowest point is in 0.7. So I write down here that the R0 is 0.7. And then I will try the same thing with the B1. I found out that the R0 is 0.7. And I open the optimization file. Here, file open for the optimization. For OA1, make sure that this is the last step. So this is 4 of 4. And then I just click here. And this is 0.73482. Then I just write down here 0.73482. And I do the same for the B1. Okay. So now what we have H2 molecule, we have the number of the distance between, the bond length of H2 from experiment and from the scan calculation with the Hartree-Fock. Here is Hartree-Fock. So A is Hartree-Fock, B is B3LYP, and 1 is the 321G basis set. So this is the first, the Hartree-Fock, and then this is the DFT from scan calculation. And then this number I got from the optimization calculation for Hartree-Fock, and this one is from B3LYP. And now, how to calculate the error? Okay, the error will be, so for A1, so our number minus the experimental, and then per experimental. Okay, enter. This is, so the error is 5.59%. And we can also do the same here, minus experimental per experimental. So the error will be the same because the number is the same. And we move to this one. So optimization minus this one per experimental value. And I will do the same with this one. So this number minus experimental value per experimental value. So now you can see from this one, from the scan, it has a same value. But for the optimization, you can see which one is the best and which one is the worst. So this has more accurate result because the number of error is the lowest one, and this one will be the higher one. But in your calculation, you will have A1, B1, and then A2, B2. So there is a lot of combination, and you can compare which has the lowest and which has the highest error percentage. And you can tabulate in here. So make the complete tabulation by yourself. And then for the report, you only tabulate the worst accurate and the best one among the combination of methods. So which one is the worst? So you can tabulate for each routine, the scan and the optimization. Okay, from here, is there any question for the report? So the first one is only explanation. And then the second one will be the list. What is the main indicator? And then the third one will be the table. And also the analysis. So the third is table and with your analysis. And the fourth one, maybe you can capture the plot and then you can list what is the similarity and what is the difference. Or you can make the table. It's up to you, table or matrix, to list the similarity and the difference between two routines, OPT, VS, scan. So you can compare anything in terms of time, in terms of maybe difficulties or the result or etc. So a lot of things you can compare between these two routines. So find the similarity and find the difference. So you make you make the comparison analysis here. And the 5 is, choose the worst and the best accurate method, and then you make the comparison analysis here. Okay. Arta, you want to ask question? Arta, you raise your hands. Are you asking?
No, Dr.
Oh. Okay, is it clear about your report? So if it is not clear, please ask. Okay, Putri.
Permisi, Dokter I have question about SCF done
Okay.
in question 3.
Okay. Let's see the question
Pertanyaan
3.
saya terkait yang SCF done itu untuk yang dituliskan itu apakah jumlah iterasi atau harus nilai yang min 1,164 itu?
Okay. The number of SCF done berarti jumlah SCF done. Jadi jumlahnya ada berapa? So it's the number of iteration, not the energy. Is it clear? Jadi jumlah SCF done, bukan energi. Ini kan energi.
Yes, Dokter
Okay. Okay,
Vera,
next question.
clearly. Thank
Okay, thank you, Putri. Okay. Okay, if there is no question, now you can perform your own calculations. So we still have like 30 minutes, so you can start to doing your exercise. So you can calculate like H2, O2, etc. And then if you find a problem in calculations, you can ask me. So I will give you like 50 minutes for calculation. So actually this is the time for breakout room, but since you have no group here, so you can perform your own calculations to check whether there is a problem or not in your calculations, and check whether you understand or not. Okay, how about the student that joined online? Is there any problem or something that you want to ask? Okay. Okay, let me check. Okay, is there any problem with your calculation? No? Hendra? Is it okay there?
Semuanya keras.
So far, it's okay for now.
Good.
We found some errors, but we can manage it.
So what is the error? Maybe we can discuss.
The one I found because during the scan calculation, the atoms are too close, the first
Yeah.
one. And the second one was, we already modified everything to set up to the scan calculation, but the error number for that we found earlier is 207 2070. That's the error number, but we already managed it. But we are not sure what happened.
The error. With this, did you perform OPT or scan? A scan.
Yeah, the scan.
And then you got the error. So you calculate the error.
Yeah, we got the
20. And then what did you change to manage the error? The step size?
So we restart from the because we restarted from the early, and I think because some of them use the same file and modify it and restarted. Just restart it, and it's done now.
Okay, so recalculate again.
Recalculate again.
Okay. Okay, thank you, Hendra.
Thank you, Dr. Ferran.
How about the student that join online? I didn't hear them. They also didn't answer me. So I don't know whether they listen to me or not.
Menarik banget ya, Bidir.
So, Olive, did you hear my voice? Olive join online or offline? So you join online or offline? Offline. Okay. So who are the one who join online? Ayo. Okay. Ayo is join online. Bintang. Bintang also join online. Devi. Okay, so offline. Galang. Wani.
Iya, Dokter Vera.
Is there any problem with your calculation? Can you follow?
I can follow, but
Okay.
uh,
Yeah.
is please to calculate.
Sorry.
Laptopnya nge-lag
Oh, okay.
sambil nge-zoom, jadi agak lambat.
Okay. It's okay. How about Arta? Bintang? Rifki? Which one is Rifki? Rifki? Okay, so join offline. Okay. Is there any problem? If not, okay, I will remind you about the assignment. So, basically, like after class, you have to submit your evidence of the group discussion. But today is special because your Malaysian student cannot join because they are in holiday. So that's why you have to submit. So make the learning journal like the and submit tomorrow night. So not today. So actually you have to submit like in the day after the class. But no, because you are not in the full team, so you have to submit it tomorrow night. So make the point by point of your learning journal, like what you learned today. I mean, like, okay, OPT or scan calculation, and discuss with your friend, with your groups, and then submit to the Hebat e-learning. So only in Hebat e-learning for the evidence of the discussion. But for report, you can submit in the UTM and also in the Hebat e-learning. So there is two assignments. The first one is the evidence of the discussion, the learning journal, and the second one is the report. So the report will contain of the answer of these 5 questions. So this one. So yeah, the report will answer these 5 questions. And in the conclusion, you will identify. So the conclusion is the answer of the objective. So the first objective is you can identify which one is the physical problem and which one the computational problem. For example, Wani said that his computer is hanged, so that will be the computational problem. And for the second is your opinion of the use of DFT calculation using 2 different routines for geometry optimization. So after performing a lot of calculation of scan and also optimization calculation, you will know. So you give your opinion. Maybe which one is faster, which one is more effective, or which one are easier for you. So you can make your own opinion based on your point of view, based on the data that you already tabulate. So that will be the conclusion of your report. So from here, is there any question for your report? Because you have to submit it next week. Okay. The most important is because you will compare for all the molecules, so you need to define the same step size. So for example, you choose 0.5. The step size is 0.5. So it will be applied also for H2, 0.5. For O2, also 0.5. So the same step size. Okay, understood? So choose the same step size. Okay, from here, is there any question for the report? Is it clear? So if it is clear, then you are ready to do your report. So, okay, please continue your calculations and discuss with your Malaysian friend. And this record will be uploaded in Hebat e-learning. So, Mbak Noor will upload it today, maybe tonight. And then your Malaysian friend will maybe watch tomorrow, so you can discuss with your group and do the assignment. Okay, and I will remind you to submit the report for the module 3. So the deadline is tomorrow. So don't forget to submit your report. Are you finished with the report of module 3? Finished? Okay, a good one. Rifki already finished his report. So just submit it. Okay. That's all for me. So before I close this class, we need to take a picture. I forget to take a picture in early of the class. Sorry. So please turn on your camera.
Are you ready, guys? One,
Wait,
two.
wait. They still open their camera. Okay. Give the best smile. 1, 2, 3.
Again. 1, 2, 3. Alhamdulillah.
Thank you, Rico. Okay, I will close this class. Thank you very much for joining. So is it okay if you cannot attend offline? So you can join via Zoom. And if you cannot join via Zoom, please let us know via email. Okay, I will close with doa. Subhanakallahumma wa bihamdika, asyhadu alla ilaha illa anta, astaghfiruka wa atubu ilaik. Alhamdulillah. Assalamualaikum warahmatullahi wabarakatuh. Okay, thank you.